Liftoff of the Delta rocket carrying Blast.
Hello, everyone. Teachers and students, welcome to Big Brothers Big Sisters Discovery Festival 2021. We are so excited to have you here today. My name is Amanda Schlindwein, and I am the Executive Assistant. Quick shout out to Nexus Brewery for letting us use the spare room in their amazing restaurant. There's great food and drink here, so please stop on by and support local business. This morning, we have David Gibson representing the National Museum of Nuclear Science and History, here to tell us how nuclear energy is used in space exploration. I'm going to kick it over to you, David. Thank you for joining us. Hey, David, if you're speaking, we can't hear you. Oh, there you are.
There we go. All right. Can you hear me now?
We sure can.
Wonderful. Well, first off, thank you for having us here at the Nuclear Museum, be part of your event. We love what you guys do. We love this particular event. My family, we always go and enjoy it. So it's cool to be part of it this year, even if it is in a virtual format, which is a little bit different, but we appreciate you guys putting this content out there. So thank you so much. What we're going to be talking about today, what we're going to be doing in here today, if you guys do have questions, I can see the chat. I can, question and comment with those there. But we're going to be talking a little bit about nuclear in space. I've got some videos that I'll show, some quick clips. If one thing that you'll want to do if you are watching at home, something that might help out is to get one of these. Now, you don't need a weird plastic coin from the dollar store, but you might want to have a coin handy or several coins handy, because we will be talking about Half-Life in a little bit, and you can kind of follow along with the presentation if you do have some coins handy. So we'll give you guys a little bit while I'm kind of introducing the program to quick reach in your pockets, get in your piggy bank, get in wherever it is that you keep that change, and get a couple coins. We're going to be talking about Half-Life. We're going to be talking about a demonstration that kind of talks about Half-Life, a thought experiment that talks about Half-Life, as well as nuclear in space. Nuclear is very important in space exploration and in space discovery, because it's one of the primary way things are powered. We see a lot of solar up in space. We don't see a lot of wind up in space. So I've got a video that's going to talk about that. I'm going to go ahead and start that video off, and then we'll come back and talk a little bit about what we saw in that video and some ways to kind of broaden your knowledge about nuclear. So I'm going to skip over, I'm going to share a screen, and I am going to show a quick video. This one here is about nuclear in space. And so let's see, let's start it off. You will probably recognize the bald guy in the video. That's me. So let's see, make sure I'm bringing the right one up here. Right here, there we go. So we're going to talk about nuclear in space and how it powers things in space. I'm going to bring this screen up. And let's see, I'm going to hit play. If you could enter in the chat there, let me know if you can, in fact, hear this one.
Hi guys, this is Mr. Dave, and I'm with the National Museum of Nuclear Science and History. What makes nuclear beneficial in the long term if we wanted to survive on Mars? Now, here on Earth, we have a couple different ways that we use as our major electricity generation. Now, I say electricity generation. Normally, when you hear energy generation, we're talking about the generation of electricity. That means to make electricity from a different power or energy source. That source can be fossil fuels, that source can be wind, that source can be solar, and those are kind of our primary ones, in addition to, of course, nuclear. A lot of these that work well here on Earth aren't quite as productive in space or on Mars. One of them being fossil fuels. Now, fossil fuels here on Earth, you will burn the fossil fuel in one way or another. The heat will turn a turbine, which will power a generator, which will get those electrons moving and give us electricity. So what about wind? Right? We see all these huge dust storms on Mars, so something's blowing that around. It must be wind, right? So there must be a lot of wind on Mars. Well, there are times on Mars where it is very windy, and it does blow a lot of dust around. But something about that wind on Mars is a little bit different. The atmosphere on Mars is about 1/100th of what it is here on Earth. So even though that wind may be blowing 60 miles an hour, it wouldn't have the pressure to power a big fan like you see, right? Those big old turbines, those big windmills that you see. Those require a lot of air pressure, right? So 60 miles an hour wind down here on Earth is pretty powerful, but 60-mile-an-hour wind on Mars is not quite as strong. And that is like this ping pong ball, right? If we were to imagine this ping pong ball to be the atmosphere on Mars, right? Which is 1/100th of what we would find on Earth. The one little ping pong ball, if it were to fly at me, it didn't have a very huge effect. Now, if we were to take 100 ping pong balls to simulate the atmosphere here on Earth and all of that pressure, it will have a larger effect. As you can see, the pressure here on Earth, that 100 times the atmosphere of Mars, will have a lot easier time affecting something, causing the movement of those big old windmills that on Mars wouldn't be quite as powerful because we don't have that pressure. So what about solar, right? Now we see these solar panels in a lot of the things that go up into space, and that is because a solar panel, once you have the equipment there, it doesn't cost anything to run. So the power comes directly from the sun with no moving parts. But remember how we talked about those big old dust storms? When you get those dust storms, they will cover those solar panels. If you have no sunlight, you have no energy. Now, nuclear is in use right now up on Mars. Our Perseverance rover is using nuclear. Some of our previous rovers have used nuclear. And what they use is a multi-mission radioisotope thermoelectric generator. And so it's able to generate electricity directly from the heat, meaning it doesn't have to turn a turbine, so there's no mechanical parts that all that Mars dirt and dust can get in and that can wear out. We can get a lot of electricity or a lot of energy for a long time using nuclear. Now, why is that important if you're on Mars? Well, a lot of times you want light to see, or you want to be able to recirculate the air to breathe, or you want heat or cooling. And those things come from the electricity or the energy that's generated from whatever power source you're using. I'm an old guy, I probably won't make it to Mars, but maybe one of you guys will, and maybe you will be using nuclear to power that mission. I hope so, and if you do end up going to Mars, make sure you send me a little note. I'm Mr. Dave, say, hi, Mr. Dave from Mars, and wish you were here, because I'd love to get that note from you someday from Mars. This is Mr. Dave with the National Museum of Nuclear Science and History. So if you do go up to Mars and you are digging around in that Martian dust, don't forget to wash your hands.
Mr. Dave, you're muted.
Okay, there we go. Should be good now. We're good to go. Cool.
Yep, good to go.
So, let's see. I think I'm done showing that one. There you go. All right, so we're good, and you're not hearing the audio from that video anymore?
Yes, that's right, just you.
Okay, perfect, thank you. So that one there talked a little bit about how nuclear is used in space and how important it is to space kind of exploration. And as you saw, even in the rover, they're using a lot of nuclear energy because of its reliability, over the long term. So this last rover that just went up, that Perseverance rover, you guys have heard all about that and made, it was a big deal in the news and all those. Now we see those solar panels that are on there. It uses solar in addition to nuclear. And that's because, as we saw there, we see a lot of dust and stuff. Well, I don't see it on Mars. I've never been to Mars, but maybe one of you guys will be to Mars someday. And like I said in that video, send me a postcard. Hey, Mr. Dave. But on Mars, there's a lot of dust. And so it's very important to have something that can continually provide that electricity, like nuclear. So the thing that they have on a rover, or in that particular rover in Percy, let's call it Percy like we're old friends, in that particular rover that they have there is called a multi-mission radioisotope thermoelectric generator. Okay, that's a lot of big words to say. What they do is they'll send up some plutonium-238, and that plutonium-238, as it's decaying, right, we're going to talk about half-life in a little bit, as it's decaying, puts off heat. Okay, that's how we generate heat in our nuclear reactors here on Earth. That's the same way we generate it up there at the first part. Now, our reactors here on Earth, we'll get it to turn a big turbine, which turns a generator, and that generates electricity. Now, if you've got all that Mars dirt and that Mars dust, you don't want to have to rely on something that's going to be able to turn and crank continuously, because dust kind of has a tendency to gum up the works. So up there on that thermoelectric generator, what you have is you have some sheets of metal, okay? And those sheets of metal, you have one side that is nice and hot, one of those sheets of metal, the other side that is nice and cold. And what happens is when you have those sheets completing your circuit, it generates electricity. So we use that heat from that plutonium-238 to heat up the one side of the shield. And that, through that thermocoupler, creates that circuit and gets those electrons flowing. Electricity is just the movement of electrons. So when we get that heat and that cool in that thermocoupler, we start moving those electrons, giving us energy, giving us electricity. Now, that up there, you say, okay, well, so they've got some uranium up there. How long is it going to work, right? Because the sun's going to be around, hopefully, for a really long time, powering solar. But how long is that little bit of plutonium that's up there? How long is that going to work? Well, that Pu-238, which is fun to just say Pu, I know, but that Pu-238 has got a half-life, or the amount that they send up there is going to end up lasting about 87, 88 years, okay? So this has got enough of that material to last for about 88 years. So this plutonium up there, they send it up there, they say, hey, you know, that rover, we want it to be up there. We're expecting to be able to use it for about 10 years. But what if it's still working? Then we can still continue to get images from Mars and get data from Mars, because that little bitty bit of plutonium, the amount that they sent up there is maybe about the size of a softball, okay? And so that plutonium can last for about 87 years, putting out constant power. So it's a wonderful power source if you are using it up in space. Now, you say, okay, well, Mr. Dave, you say that it's going to last 87 years. How do you know that? Okay, so now this is that part that I was talking about that you might want to find those pennies for, that change for. We're going to talk about half-life, and we're also going to talk about this box right here. We're going to talk about a little thought experiment that was put on or was imagined by a gentleman, Schrodinger, which is a fun word to say anyway, but it was imagined by Schrodinger. And Schrodinger was, he was working a lot with teams that were working and discovering a lot about radioactivity, right? Which radioactivity is what happens when, like, that plutonium, as it decays, it puts off radioactivity, okay? So he was discovering a lot of stuff about radioactivity and discovering how long something would be radioactive, which is very important. And what we call that is, we call it the half-life, okay? Now the half-life says, okay, if I have this much material, it takes this long for half of that material to decay. That's half of the life, okay? Now that's very important in what Schrodinger was thinking, and when we're talking about half-life and how we figure out how long something's going to last up in space, is to know, okay, well, what's the half-life of something? As I said, we imagine that plutonium there, or they've calculated that plutonium that they put on Percy is going to last for 87 years. That's a long time. So Schrodinger, in trying to explain how a half-life works and how on a quantum level, right, which quantum is when you're talking even tinier than an atom, okay? Quantum physics, quantum mechanics, all of those things are things that you're talking about on a scale even Ant-Man has a hard time saying. So yeah, if you are a comic book fan, you know that Ant-Man went into the quantum realm, right? Now, in reality, we all live in the quantum realm. We're just not able to observe it, okay? So what Schrodinger said is, okay, well, if we can't observe it, because this quantum realm is so tiny and so unpredictable, how would I describe how random this really is? Now, we use the word random in social media, or I just had this random thought. We hear it all the time, but really, I've never had a random thought. And I sit there thinking about, what if this puppy were pink? And, oh, L, right? So I think about these things and you're like, oh, well, that's random. Well, it's not, because our minds have got to lead up to that some way, right? But when you get to that quantum realm, that little bitty realm, you do have things that are actually random, okay? Now, circling back to half-life, we've got that half-life, right? Plutonium, that Pu-238 in space is going to last 87 years. Let's talk about a different element or a different isotope, okay? Now, I say isotope and I say element. Now, an isotope is an element out of balance, okay? That means that the protons and neutrons in there aren't matched up, and so we've got an out of balance. Now, everything in the universe is working its best to find balance, right? So if we take a different isotope, in this case, in Schrodinger's case, it's called nitrogen 13. Okay, We've heard of nitrogen, right? Liquid nitrogen, gets stuff really cold. I'll use it in demonstrations here at the museum where it puts steam all up in my face. Liquid nitrogen is great. This nitrogen 13, this particular isotope, right? This element that's out of balance, this isotope has a half-life of 10 minutes. Okay. Now remember when we're talking about that Pu-238, we have 87 years worth of consistent energy that we're getting out of that. This little bitty nitrogen one, we've got 10 minutes. Okay. Now what that means, okay, with Schrodinger here, is that in 10 minutes, if you had just one little bitty atom of nitrogen 13, that one little bitty atom in 10 minutes may or may not decay. He's like, okay, well, why is that important? No, really. When I flip this coin, okay, to us, this is as close to random as we, could kind of say, okay, well, yeah, that's random, but really, there are very tiny factors that would say, okay, well, if I flip this coin 48,000 times, I would end up with more heads than tails, because the way that the air catches, there are little bitty factors that change things. A true 50-50 chance is impossible except in that quantum realm. And that is when you've got in 10 minutes, one atom of nitrogen 13 may or may not decay. And to really prove that randomness, we didn't have a way of showing it. We can get pretty close, and we'll do that with some change here in a minute. But with quantum, it's random. No, really, anytime in that 10 minutes, I could have this nitrogen 13 and it could decay the second I pick it up, or it could decay 10 minutes later, or it could just not decay. So that's as random as this one little thing can be. Now, this was kind of confusing Schrodinger. He's like, yeah, well, how could it really be that random? He even proposed this particular experiment to another guy that maybe you've heard of that's pretty famous for thought experiments. His name is Albert Einstein. Now, Einstein actually quoted this experiment as the one he took to his grave, as the one that he could never, it just blew his mind, okay? And we're gonna not actually do it today, and you'll see why. We're gonna simulate Schrodinger's experiment. So we are going to simulate it. And I say simulate it because if you see on the box here, it says caution, live animals, maybe. Now, no animals are hurt in this demonstration. I do have in this box very cute little stuffed kitten. Yeah, I have a cute little stuffed kitten. Now this one here, my daughter actually made for me when I said I was going to do this Schrodinger's experiment. She's like, Dad, let me make you a cat, give me a sock. So she gave me a sock and made me this cute little kitten. I really don't want to have to kill this kitten. Yeah, and so that's why I'm saying this is a simulation of that experiment. Now you say, well, this Schrodinger, was he just killing cats left and right? No, he was not. This is a thought experiment, meaning this was something that he proposed as a way to explain something. Okay, a lot of Albert Einstein's experiments were also thought experiments. That means they were never even really conducted by Einstein himself. Some of them have been now that science has progressed. But a thought experiment is something that is a way of explaining the way something works and the science of the way something works without ever having the materials or having the wherewithal to go through it. And in this case, we really didn't want to kill any cats. So we've got this cute little cat here. And this little cat it doesn't have a name yet. And so that's kind of sad. We need to get a name for this cat. So if you are watching on YouTube, or if you're watching, in this Zoom meeting here, you can chat and maybe we'll figure out a name for this cat by the end of this. I can only see where I'm at the chat that is in the Zoom meeting. I'm not able to actually see the chat from the YouTube stream. So if that is the case and you are putting something on YouTube, maybe I'll check it out later and I can comment, whether the cat was named that as we go along. Okay, so we've got this little kitty cat. This is a large part of the experiment. So we're going to set this little kitty cat here with no name, had kitty cat. We're going to set him right here on this table, okay? I'm going to take this piece of paper. I'm going to move it right over here so it's not such a distraction. The other things that have to do with this experiment, yeah, this is a hammer. This is a hammer, and this is a cat. Remember how I said this was kind of a, we don't want to do this in real life? Okay, now, before you get any ideas, Schrodinger did not propose, even in this thought experiment, that the hammer would hit the cat. The hammer does not hit the cat in this experiment, okay? It's actually kind of worse. I'm just saying. So what we've got here, in addition to our cat, and hey, I have a mouse. Cat in it. Okay, this is just my computer mouse. All right, so in addition to our cat and our hammer, okay, we have this little guy. Okay, now this little guy here, what we're going to do is we are going to have to use our imagination. This is a radioactive source. If you just heard that big loud bomb noise in the background, we're okay. We are live in the Nuclear Museum right now, and that is one of our exhibits. So this thing here, okay, we're going to imagine is that nitrogen 13 or N13 atom. Okay, now this is actually a radioactive source. I'm going to show you because I've got this guy here. Another part of Schrodinger's experiment. This is a Geiger counter. Okay, a Geiger counter is something that counts the radioactivity that something puts off as it's decaying. So on this one here, if we were to turn this guy on, we'll see if you'll be able to hear. Can you guys hear that little beeping noise? Nitro cat. Oh, I like nitro cat. Yes, I do like nitro cat. I might have to pass that one on and see how that one does. Nitro cat sounds pretty good. What do you think, Cat? I think he's going for nitro cat so far. Okay, so we do have this little thing here, and it is detecting that radiation. This is a radioactive source. Now, this is not something that is dangerous. This is actually the element from a smoke detector. So you've got this in your house. You've got this all over the place. But when you're listening, every little beep there is one decayed atom that is giving off radiation, allowing this to detect it. Now, that's very important to me and NitroCat because we're going to put this out here. What Schrodinger proposed was we have one nitrogen atom. Remember, one atom, which would mean one beep. Now, that beep can happen anywhere in that 10 minutes or not happen at all. Remember, we've got that quantum randomness. So this little guy here is representing our nitrogen 13. This is representing a hammer, and this is now representing NitroCat. Okay, so we've got our device here. What this device was or represents is when Schrodinger said, okay, so when I've got my nitrogen 13 and I've got my counter, when I sense that, or when this counter senses that radioactive decay, I want this to swing the hammer. So this device actually swings the hammer when we get that radioactive decay, or if we get that radioactive decay. Now you say, Mr. Dave, I thought that the hammer wasn't going to hit the cat. It's not. It's not. It's worse. In this vial here is a poisonous gas. Now, this gas will instantly kill this cat. Remember, this is a thought experiment. I am not a cat killer. I have a little kitty cat at home. I love kitty cats, but this is a way of experimenting or demonstrating that half-life principle. So we've got our poisonous gas. Now, instead of this hammer hitting the cat, the hammer will actually break the vial of poisonous gas, sending NitroCat to NitroKitty heaven. So we're going to put our vial in the box. we are going to put our device in the box. Oh wait, first we have to put our isotope. This is our nitrogen or N13 isotope into the device. We're going to put the device into the box, hook up the hammer, hook up our Geiger counter. Put NitroCat in the box. Okay, so I'm going to put NitroCat in the box. Now, it's okay, NitroCat. Now, when I close this, our 10 minutes will start. Now, at any time, that atom could decay. This is the most random thing, with the true use of the word random, that we as humans could ever fathom. Because right now, that cat could be dead. Right now, that cat could be alive. Now, this is the tricky part. In Schrodinger's thought experiment, there was no way of knowing. Okay, now this actually branches out in a couple different things. One, this is showing that right now, this cat, well, let's see, is it alive? No, right now this cat is definitely dead, right? Because we know that well, no. Okay, so this is the problem. This was Einstein and Schrodinger and many scientists since then dilemma. Right now, with no way observing, this cat is now dead and alive. Or this cat is dead or alive. Or wait, maybe the cat's just dead. No? Okay, so this is the problem. There is no way of knowing, which means when you get to that quantum and you get to those experiments with different dimensions, again, I am a huge comic book nerd and movie nerd. I love these multi-dimensional and the Spider-Verse and Loki going to all these. Yeah, anyway, this was what one of the ideas that said, okay, well, now we have two parallel universes. There is a universe in which this cat is alive. There is a universe in which this cat is dead. And that was Schrodinger and Einstein kind of started proposing and kind of blew their minds. And, you know, you get all the way to, you know, some of your more contemporary scientists, and they say, okay, well now, okay, but there are also all of these string theory, and you can get into all kinds of crazy stuff from this right here, when really what he was demonstrating is a half-life. Okay, so we're going to leave this little kitty cat in here for 10 minutes. We put them in there at 11:30. So at 11:40, we're going to try and pull this cat out and see what happens. So I hope he's okay. Little Nitro Cat. He's finally got a name. So what we're going to do is now go ahead. If you're watching, grab your coin, okay, or many coins, multiple coins. Now, really, to do this one best, you'd want about 50 coins or 100 coins. Another thing you can use are like game tiles, Scrabble tiles. That's a wonderful one for doing this demonstration here. So what we've got, I might have to cheat a little. I forgot the rest of my coins in the box. I'm gonna leave them in the box. I'm scared. I'm nervous for the poor Nitro Kitty. I'm gonna leave them in the box. I'm gonna use these coins here. We've got plenty. We're good to go. So if you've got your coins, what we're going to do is we are going to determine a half-life. Okay. Now, if you've got 50 coins or you've got 100 coins, that's awesome. If you are in a classroom right now, okay, if you are in a classroom, it would be really cool. And the way that we'll do this in a classroom is give everybody 1 or 2 pennies or 1 or 2 Scrabble tiles or checkers or anything that you can flip. And then we'll use that as a group project. So if you are in a classroom, if you are able to kind of communicate over to the Zoom meeting here, we would like to know if you are in a classroom, because this is a fun way to do in a classroom. Or maybe if you're a teacher watching this, you're like, hey, I can try it in my classroom later. There you go, because we're going to talk about a half-life. Now, remember, that plutonium, Pu-238, up on Mars right now, we said is going to give us power for 87 years. How do we know that? This is how we know that. Right now, I have 1, 2, 3, 4, 5, 6 coins. 6 coins, okay? On these ones here, when we purchased them, we noticed something very special about these coins that will make this demonstration fail every time, and that is that the coins we purchased have heads on both sides. So what we did was we drew some X's on one side. So I've got heads and X's, okay? Now, heads, we're going to imagine that the cat is alive, or we're going to imagine that our isotope has not decayed. So this isotope is not decayed. And what we're going to do is we're going to talk about a half-life using 6 coins, okay? So with our 6 coins here, if you've got some at home, you can play along, and I would love you to play along. If you have 1 coin, you can try it out. If you have bunches of coins, you can try it out and carry it on a little bit further. So we're going to start with this 6, and out of the 6, I'm going to flip them, okay, and see. Okay, right now I've got a heads. This one here is heads, so this one stayed. I'm going to flip this one here. Oh, this one ended up with an X, which is tails. Now that means that this one here has decayed, okay? We're discovering the half-life. So this one here, we've got heads. All right, so this one did not decay. And, oh, heads, this one did not decay. And there we go. Ooh, tails, this one did decay. And heads, this one did not decay. Now, you say, okay, well, Mr. Dave, you only had 2 that landed this way and 4 that landed this way. Yep. Now, what you can see if you have a large classroom or even a medium-sized classroom with a whole bunch of students doing this, or if you're at home doing this one here, if you take a piece of paper and you take a pencil and you say, okay, so far, 2 of mine have decayed, I've got 4 left. If you start a graph, okay, and your next roll or your next throw, you say, okay, 2 more decayed and I've got 2 left. Well, now you're going to see, okay, we're discovering something here. We have a nice little smooth curve on our graph, because if you've got enough of these, and the more you have, the smoother your curve is going to be, you're going to notice that we can discover that half-life by the curve. It says, okay, so by this point, this is going to decay. So let's see on our next 2 here. Oh, I put that one really high. So this one stayed. Okay, so we're good there. Oh, this one decayed. Okay, this one's over here. This one here. Whoop. This one also decayed. Okay, and this one here. Ooh, this one also decayed. So we would notice that we went down from that 6, 4, and 1. Now let's see how long this one takes to decay. Will it decay the first time? It did not. Will it decay this time? Whoop. Oh, it did. Now, when we relate this back to our plutonium in space, when we relate this back to our kitty cat in a box, we know that, okay, so this one took a total of 5 rolls for it to decay, right? We knew that we were at our halfway point at about 3 rolls, right? Because we were in between that 4 and that 2. And so we can say, okay, well, we've got about this long of a half-life for my 6 coins. Now, remember, if you had a whole bunch of coins, instead of doing them individually, just take them, put them in a cup, shake them up, throw them out, okay? And then you've got your coins all on the table, your ones that decayed, put to one side, the ones that did not decay, put to the other side, okay? Now, that shows us a little bit about how they predict on how long that plutonium is going to last in space or in a reactor, okay? Now, in these reactors, they'll do things, they'll bring molecules closer together or further apart, or they'll insert rods that can slow things down, graphene rods and other isotopes on these rods that can kind of absorb some of this radiation. And so they can kind of control how long and how fast these reactions are happening. Now, when you're up in space with these these thermoelectric generators, there's a little bit less control there. So you got to kind of say, okay, well, this is that half-life. This is how long that's going to last in space. Now, to kind of relate it, oh, it is now 11:40. I was trying to put it off. I didn't want to talk about it. I was a little bit nervous. It is 11:40. We're going to see what happens with NitroCat. Okay. So right now, NitroCat is dead and alive. Dead or alive. Just dead or just alive. Let's see. I'm kind of scared. My daughter made me that little thing. I'm going to be sad. When I open this, if you subscribe to the Interdimensionality, we're going to know which dimension we ended up in. Oh, yay. Okay, so NitroCat is okay. Whew. I don't know if you can see my bald head sweating. Yeah, NitroCat is okay. I am so glad that you survived NitroCat. I'm going to close that box before anything happens with that gas. Now, okay, wait, there wasn't really poisonous gas in there, just to be clear, okay? It was really just an empty vial of normal air, right? But NitroCat did survive, so yay, I know, thank goodness, yes. I know, I was pretty nervous, I was gonna be sad, but NitroCat did survive, okay? But in this here, the second I close this, that same little nitrogen-13 could have decayed. Again, you've got that half-life. So in the randomness, there is a pattern. And that's what's so confusing, is because you can say, okay, well, and when you get down to 1, it's random. Now, if I were to have millions of those isotopes, just like those coins, I would be able to graph that out, and I would be able to say, okay, so we know that any one of them could decay at any point, but a lot of them are kind of decaying at this rate, and that's what ends up giving us that half-life. So that's the quandary, that's the craziness of quantum mechanics and quantum physics, is that the randomness has a pattern. And as oxymoron as that sounds, that is how they use that half-life equation to say, okay, we got Percy up there. Percy should live to a ripe old age of at least 80 years old. At least she'll have the energy. Now, I know me as an old man with kids and a job and all those kind of things, my energy kind of decreases as I get a little bit older. But with that plutonium there, it's going to be consistent and predictable all the way up to that 87 years. And that's how they use nuclear in space. Now, I've got one more quick little thing that you guys can do at home. And this one here is kind of like our Schrodinger's cat, except right here after Halloween, maybe you guys have got some of these guys around. Little bitty spiders, okay? They're little bitty plastic spiders. They're not real spiders, okay? These are plastic spiders. This is a fun way at home. You could say, hey, mom, dad, or hey, students, or hey, kids. I don't know why they hate kids, but anyway, that was a little bit SpongeBob of me, sorry. But now, this is a fun way that you can demonstrate this same principle without going through all of the things of Geiger counters and boxes and cute little stuffed NitroCats. And you can get these little spiders. You can get them at the store. You probably have some stuck in a corner somewhere from Halloween decorations. Get them and put them in a container that you can't see into, okay? Now, for the sake of this demonstration, we're going to say if our little spiders are right side up, meaning their legs are down, then they're alive. Yay, they did not decay. If our spiders are legs up, then we know they did not make it, right? We have a couple less spiders. So in this, for instance, I'm using 4 of them, and I have 2 that are green and 2 that are black, okay? Now, you don't have to do that. If you find one little spider that'll work, you can do this also with your coin and a cup, okay? And cover that cup, and it's a very easy way to do it without even having to find anything. But we're going to do it with Schrodinger's spiders. I like to call this one Schrodinger's spiders So I'm going to put our little spiders into this container here. Now, I'm going to shake this. Again, do not use real spiders, because if you use real spiders and you put them in a little container and you shake them, yeah, they're going to jump all over you. Yeah, we're going to be really sad. So with these little guys here, we're going to shake these up. And what that is doing is just creating a more random situation where we're going to have some with their little feet up, meaning that they did not make it, and some with their little feet down, meaning that they did. So I'm going to go ahead and open this up, and let's see. So in our first demonstration here, I would like to say that this is completely random because, as I poured them out, they changed, but we have two that are alive, one black one and one green one, and two that are not. So this is a fun way that you can talk about that Schrodinger's demonstration at home. And so I'm wrapping all of this up here. I know you guys have got some questions. If you'd like to put them in the chat, if you would like to talk to them through my funny little earbud thing, however that works, I'm going to open it up this up to questions. Again, I want to say thank you guys so much. Thank you, big brothers and big sisters, for all that you do. And thank you for letting us be part of this event. I will open it up to some questions if you've got them. You can put them in the chat right there, and I will just stand here. Oh, there we go. Or you can, hello. Hi, nice to see you.
David, first of all, that was a really, really great presentation. Thank you so much.
Thank you.
So our first question comes from Caden here in Albuquerque, and he wants to know where plutonium-238 comes from.
That's a really good question. Now, we don't quite have enough time to explain all of that question, but I'll give you kind of the beginning of the answer. We have uranium that occurs naturally, and you can process that. And there are certain places where plutonium occurs naturally, but it's very rare. But it's actually a processed kind of version of plutonium. I mean, of radium. Of uranium. There you go. So when uranium is processed, we can get plutonium as a byproduct. And I'm glad that you asked that, because this plutonium-238 is kind of a fun game to end up getting, because if you ended up with plutonium-240, which is a little bit different. So while you're making that, or refining that uranium, if you end up with plutonium-240, it will kill a nuclear generator. So that is a wonderful question. And yeah, it's something that we don't really come across in nature. We get it by refining or by processing uranium. So thank you for that question.
Thank you, David. So Bobby in Farmington asks, why do atoms decay?
Why do atoms decay? Now that, again, is a wonderful question. That one I can answer a little bit easier and a little bit quicker. A normal atom, okay, your atom, like you see most of them on your periodic table, all the way up to bismuth, is stable. And what that means is you've got three parts of an atom. You've got your protons and your neutrons and your electrons around the outside, okay? Now the electrons around the outside don't really affect the stability, but the protons and the neutrons do. And so if your protons and neutrons are out of balance, meaning that you've got more of one or more of the other, it's going to try and find balance. And so what it's going to do is it's going to do what we call decay. Now that decay is, there's different ways it can decay by alpha, beta, gamma, different radiations. But what it's going to do is give off protons or protons or neutrons in order to try and balance out and become stable. They decay because they're not stable. It's like if you have a teeter-totter and you have three kids on this side of the teeter-totter, one kid on this side of the teeter-totter, the one kid's going to be shot up into space. They write another way to get to space. But if you have two on both sides, you're going to have stability. So that's what that atom is shooting for, is stability. Thank you, Bobby. Oh, I'm sorry, I can't. Oh, there you go.
Sorry, I was muted.
You're good. You're good.
So our last question is from Brittany, and she wanted to know, so there's lots of work being done on Mars with plutonium, sort of exploring and doing all of this work. Are we doing this on other planets, on maybe our moon or other moons?
Actually, in space exploration, like our moon, other moons, not really yet. And I say not really yet because there are things in space that are nuclear powered. So it isn't just on Mars. The lunar rovers have also, which are our moon rovers, also using nuclear power. The ones that were strictly solar, we saw kind of die out a while back because they fell into a dark spot and got dusty. And so now lunar rovers, a lot of our things that are in space are at least have a nuclear component. That's an awesome question. Yeah, so it's not just Mars, it's all over space. Not all over, but as far as we can get. If you hear that squeaking noise, that's one of the exhibits here in the museum. We're not being attacked by bats. And I don't think it's nitro cat.
Thank you, David. That was actually all of our student questions. Do you have any final words to end on?
Just thank you. Thank you. Thank you again, big brothers and big sisters, for putting this on. Thank you for working with me, and getting everything rolling and those kind of things. And thank you guys for watching and for supporting big brothers and big sisters. You guys are wonderful, and I'm so proud and so happy to be part of this. So thank you from the National Museum of Nuclear Science and History. And if you've ever watched any of our YouTube or anything that I put out on the internet, I always end the same way, which is don't forget to wash your hands.
Thank you, David. Wise words. Don't forget to wash your hands.
Don't forget to wash your hands. There you go.
All right. Well, thank you so much to the team at National Museum of Nuclear Science and History, particularly David, for this amazing presentation. And to the teachers and the students, thank you for stopping by. We have 2 other demonstrations today. We have the education plan at 1 p.m. to talk to students about the importance of saving up for higher education with a fun Jeopardy game. And then Math Hoops will be holding a special presentation for educators at 6 to do a demo of their board game. Thanks again to Nexus Brewery for hosting us here. They are a great business. Thank you to the schools who are participating, and thank you to the National Museum of Nuclear Science and History. Thank you.
Thank you again. You guys have a wonderful day.
Oh, you too.